So probably the most important thing I can tell you in this talk, especially to younger members in the audience, is that there is some opportunity for, so we're hiring. So if you're interested or looking for a job, recently we started a new lab at Caltech focused on math and AI. And it even comes with specialization. So if you apply for grad school or some of your students apply for grad school, there is like a radio button you can hit. Next to algebraic geometry, topology, now there is like AI research. So that's part of it. I'll explain in the talk some of the statements that are written here. So for example, we specialize on very hard, deep searches, and I explain why that's important or necessary. You can think of it as like playing chess on an infinite board. So that's going to be like main theme of the talk. And also the website is easy to find. There is this logo, math plus AI equals AGI. So AGI stands for Artificial General Intelligence, and everybody has been racing to that a couple of years ago when the lab started. So now actually it has to be changed to something like math plus AI equals ASI, but it's coded, so it's hard to change. Anyway, okay, let's see how this works. Okay, here we go. Okay, so I'll tell you several stories in this talk, and this one is very interesting. It's a story of a horse that lived 100 years ago, and the name of the horse is Clever Hans. And the horse became famous because it seemed like it's really good at reasoning, including mathematical reasoning. This is, of course, the topic of our talk, so that's very relevant. And this person, the guide or MC in the show would ask questions, something like, was ist 5 und 5? What is 5 and 5? And the horse would tap 10 times and everybody would applaud. So that's pretty cool. So the horse, like I said, was very famous. So it went around, made presentations. I think it's actually more famous than me. I go around, make presentations, but I don't expect my name or my work to be remembered 100 years from now. But the horse certainly has its legacy. But the legacy is kind of tainted in the sense that there is, in AI research, there is so-called Clever Hans phenomenon, named after this horse. And phenomenon is not really that good. So it took people 3 or 4 years to actually do research on it. And they, at some point, realized that if the horse cannot see this person making the presentation or asking questions, the horse cannot answer the right question. So something was fishy, and then they started digging into it and realized that something is off. So what happened is horse actually was very good at picking subtle cues that the MC or the person, the guide, would actually present, like a subtle nod or something like that. So in AI research, this Clever Hans effect refers to something negative, almost like having test data in your training set. So it's not that great. So maybe I don't want that legacy. But anyway, I was thinking, while reading the story, what is the modern day equivalent, or what is the, at present, 100 years forward, the closest analog of Clever Hans, right? And this was happening, again, I'll tell you many stories, but this was in summer 2025, half a year ago, and this was a very exciting time. So Harold and I were working on something trying to help AI solve IMO problems, and people were excited about like mathematical reasoning going to like super intelligence and all that. And another thing that I was involved in was benchmark creation for Frontier Math with Epoch AI. That's another company in Bay Area. And several people were involved, including myself and Greta. And since then, we have this like joint chat on Signal. And usually I don't participate, neither is Greta. We're usually very quiet in the chat. But at some point, she shared a very simple example like that. So I don't remember, I don't think it was exactly this. I think this is my iteration. But anyway, what piqued my interest is that it was so basic. You basically ask a question, which is like less than a line. And we're not talking about IMO problems. We're not talking about research level math. We're talking about very basic arithmetic, like what is 9.9 minus 9.1? And at that point, GPT-4o was one of the legacy models, very famous and so on. And It's stochastic, it's not always consistent, but if you would query it 10 times, 7 out of 10, it would probably give you this answer, which is different from 0.8. I hope that's the answer you got, but it would for some reason tell minus 0.2. And actually it's interesting. It's interesting to think why this happens. From AI research perspective, there are at least 2 answers which are very important to what causes this. And we'll come back at least to one of them later in the talk. But my point here is that and of course, the trick here is that we added a decimal, like this additional zero in asking the question, and that sets everything off for some reason. So anyway, so later in the talk, I'll give you more evidence why modern days LLMs are not necessarily, I mean, we should distinguish questions like retrieval and real reasoning. So, or search versus real reasoning, and this is good illustration. So in the talk, I'll try to ask the following question. What will it take for AI to outperform human in mathematics? And by mathematics, usually we mean different things. So from the beginning, I want to establish kind of basis. And I think you all agree that there are many different levels and gradations. So in previous years, it took about 1 or 2 years for AI systems to go from elementary school problems to middle school, then to high school now, reaching level of these competitions. It's non-trivial process, so it actually takes a lot of hard work to push it like 1 level down. For instance, at this year's IMO, not a single system was able to solve all 6 problems, so it's actually non-trivial. It's hard work, and that's where general purpose tools roughly stop. But the hierarchy, of course, continues. So then we have graduate level problems, hard graduate level problems for which, if students solve them, they get PhD. Then we continue to problems which are like hard for students, but researchers, professional mathematicians can do reasonably well. Then we get to problems where even professional researchers struggle. And then we go to really hard questions such that at a certain point, if you solve them, and if you're younger than me, then you may get a Fields medal, things like that. So the question in this talk is about this part of the hierarchy, about this part of the diagram. So currently we are very far from that. Again, general purpose tools are here. I'm asking questions about this region. And I want to ask, what will it take for AI to be here? From a very constructive point of view, not to criticize anything. I mean, currently we're very far, but rather, what do we need to do as AI developers to get to this point? So that's what this talk is about. So what we are missing and what needs to be done. In other words, what will bridge this gap? There are many other potential takeaways you can take from this. For instance, I mentioned that it takes about 1 or 2 years to go from each stage to the next. So if you try to extrapolate, you can get your like prediction when it will happen. I don't want to make that prediction because there are lots of unknown unknowns in this process. So on the one hand, as we go further down, we run out of training data and so on and so forth. On the other hand, there are more and more people joining this effort. So there are like lots of pros and cons either way. So I think speculating is just a waste of time. But another comment I want to make is that I've been working on math and AI for about 7 years. And honestly, I'm not convinced that we'll get here. So part of me asking the question is being genuinely skeptical that can we even get there with imaginable techniques, or what kind of breakthroughs we need? And part of the point of this talk is that we actually do need some breakthroughs. So since I'll be talking about hard level mathematics, it's important to quantify at least somewhat what we mean by hard math problems, right? So I don't have a good answer to this question, but for the purpose of this talk, I usually say that one metric is if a problem is famous enough, so many enough mathematicians tried it, so it's really kind of broad at least, and it's open for many years, and we cannot solve it, that makes it hard. So there are lots of problems which are open, and I came up with like 2 weeks ago and cannot solve them, but unless many people tried it, it's probably not objectively reasonable to call that a hard problem just because Sergei cannot solve it. Right? So therefore, I think this is somewhat objective metric, namely the number of years it remained open if it's a big enough problem. And Millennium Prize problems fall in this category as well as some other ones. So another way to quantify measure of hardness is the following. So getting a little bit closer to like AI research, So in mathematics, we do a couple of things. If we know what we expect to be true, we try to prove it rigorously. We also try to conjecture things and refute these conjectures. So this helps us to refine understanding and then formulate hypotheses that we want to show to be true. But once we're already in this proof stage, then the goal is basically to generate a sequence of logical steps, which can be totally rigorous in a formal language, such as Lean-Cock or Rock, Isabelle, and others, where you go from A to B. So A being hypothesis, B being the goal that you want to show. For example, for Riemann hypothesis, we know the assumptions, we know the destination, we just have to find sequence of logical steps that proves it. And we don't have that sequence. So with formal languages, this became really nice, effective search process for this path in the space of logical steps. And this is how it looks like. It's kind of a mixture, if you wish, of computer programming language and natural language. It's somewhat readable, but you have to get used to it. And if it compiles, it can run very much as a program. Then everything is good. It checks out. The proof is correct. Or at least, again, there are caveats here, but I'm not going to touch on. So from this point of view, the examples of theorems that you see on a screen, their proofs, these are pretty easy statements and theorems. And what's going to be different for hard theorems, such as Riemann hypothesis, whose proof we don't have yet, is that their proofs will be much, much longer. So another metric sort of on complexity or difficulty of mathematical problem is in this, how hard is it to find the sequence of steps from A to B? But notice that it resonates with the title of my talk. So finding solution in this case would be finding a path from A to B. So it's a search problem. And what makes it hard is that it's a deep search because the distance or path from A to B might be long. And again, we'll come back to it in various versions. So this is another example, illustration of a problem where we try to look for examples or counterexamples. So this problem is from extremal combinatorics. And the problem is to identify sizes of complete graphs, let's say on n vertices, and find n such that given bicoloring with either red or blue of its edges, you can always find either red subgraph on some number of vertices or blue subgraph, complete subgraph on some number of vertices. So the precise statement here is not that important, especially if you haven't seen it before. But I want to illustrate what it takes to find that this number is 18, for example. So everything in green is what we know, and in this yellowish or orange is the range which we don't know yet. And here, to identify that this is 18, we have to show that 17 is not a good fit. So in other words, for 17, this condition that I'm trying to satisfy is violated. And it actually is, but the way it's violated is that it's only one coloring out of 10 to the 26 that violates it. So it's like a needle in a haystack. It's a very subtle, delicate thing. And if you ask, again, think about this 9.9 minus 9.1, ChatGPT to find it for you, nothing is going to happen. It's not going to find. So this is another example where we look for examples or counterexamples. And it's also a search, but it's a needle in a haystack, also search. And the previous example was that proof was long and it was very deep in the search space. Here, example is very sparse. It's somewhere there like a needle in a haystack, 1 out of 10 to the 26. So this is a huge number. It's not like 1 out of billion or million. This is 1 and 26 zeros. That's pretty crazy. This is an open problem, and I'm pretty sure that someone who solves it, or at least even part of it, deserves Fields Medal. In fact, Erdos mentioned that so this Ramsey number is R44, and he said that if aliens come to Earth and ask us to give them this R55, the next one, we should gather everyone on the planet and try to solve the problem, and then maybe we have a chance. But if they ask us for 6.6, we should just surrender. So that's how complexity grows in this range. So it's very fast. So this fast growth is something. So see, describe both types of processes proving things as well as finding examples and counterexamples as search problems. And as title of my talk indicates, that's how I look at mathematics these days. So once you have this hammer, everything looks like a nail to you. So now all hard problems look to me as search problems in some space, be it space of logical steps or searching for certain conditions satisfied by instances like in Ramsey numbers and so on. So many of the things I'm going to present to you are precisely of this kind. Now, why is this cool for AI? So AI has different branches, and one of the coolest, at least in my opinion, that's really branch responsible for playing games. So that's the one which you've read about in terms of chess, Go, and other games, is called reinforcement learning. What it does, it basically builds an agent, some neural net that interacts, makes steps, and interacts with environment, receives feedback, and corrects itself. So everything about autonomous vehicles and so on, that's reinforcement learning. So look, this seems pretty cool because this robots, they basically play games, right? So they search, for example, they can search for a way out of labyrinth. Think about going from A to B. That's perfect, right? So in that sense, it looks like amazing feat. And that's actually true. But my question now will be, okay, what will it take to train these robots to do really well on these really hard problems where it's hard to find path from A to B? So that's why I'm saying to kind of make complexity of this problem comparable to research level mathematics, really hard one, we have to make the size of this maze to be megaparsecs and very complicated. Anyway, we'll get there. But if you haven't seen reinforcement learning before, this is beginning of the modern era of AI. This is before AlphaGo and things like that. So if you are to try to build these robots, you have to go in a store and ask for a menu of options. And options include choice of environment, algorithm, and architecture. And this is about choice of algorithm, namely, it's like brains of the robot, how they think. And one of the modern algorithms came from DeepMind. There is now a beautiful movie about it, about Demis and his story. And since this was one of his first babies, it's actually prominently featured in the movie. And at that point, like I said, it was before Go and chess and things like that. So people were playing Atari games. See, I told you reinforcement learning is fun. It's playing games. And that's really true. So a robot is supposed to learn how to interact with the environment, receive feedback. In all of these games, there is an actual score. That's perfect feedback. And they train to try to do better and better. Okay. So just from pixels, pixelated screens, this algorithm called DQN, that's one of the basic choices, managed to learn how to play. And again, it wasn't a straight journey. It's not like it happened easily or overnight. If you watch the movie about it, about DeepMind, you'll see that they struggled. In fact, it didn't work, and then the usual thing. But anyway, this is one of the choices you can make. By now, it's considered very basic. It's very much like Honda Civic. It's very reliable. It's easy. It runs on your laptop. You can build it in a few. Okay, that's one of the choices. I'll discuss some other ones later in the talk. So over the years, I tried to do many different projects involving AI and research level mathematics, kind of trying to build the intuition, what works, what doesn't. And this is one of the problems. In the talk, I'll tell you about several such projects. And this is one problem from knot theory where you have to decide if this complicated looking diagram, this one is not complicated, but you can make it much more complex, is equivalent to this unknotted diagram. This is a very nice problem, very much like you can think of it as a game. This could be a given state of a chessboard. The moves you're allowed to make are called Reidemeister moves. They move the strands a little bit in local positions. And the job or question you're asking is, through the sequence of predefined moves, can you get from A to B? Again, very similar to a search, many other searches that I'm talking about. Okay, so this is a game, and yeah, looks ideal for something like reinforcement learning because number of moves is very small. These RL algorithms like it when the state space is large, but number of moves is relatively small. So these three moves could be like moves of joystick, if you wish. Very, very simple. And the reason I started thinking about it, it was actually one of my very first projects in this domain by now, maybe 6 or 7 years ago, is that the traditional method, so I came to this from quantum topology, where the goal is to develop invariants, theoretically, invariants of knots to distinguish them or answer questions like this. And as a quantum topologist, I actually never ventured much out of something like 16 or 20 crossings. Everything we would do, in fact, I would teach courses, and it wouldn't occur to me that everything I do is with so few crossings, because number of knots, even basic knots, grows very, very fast. Or if I want to compute John's polynomial, then computational complexity of it is growing so fast exponentially that we hardly can go beyond this something like 16 crossings. Whereas the questions we really want this quantum invariance to answer from low-dimensional topology point of view, where the story becomes interesting, is in the range of, I don't know, 50 crossings or 100 crossings. That's where the story begins, but most interesting examples are actually further down. And then I was thinking to myself, okay, fine. So if I'm trying to compute this quantum invariance with traditional techniques, then this complexity grows exponentially. Suppose I assume Moore's law, which means that compute also doubles every couple of years. So it means that if this year we can compute, say, 16 crossings, next year we have 17, and so on, because it's like log versus log or exponent versus exponent. And then I need to get here, which means I need another 50 years. And I'm now becoming very skeptical of my ability to reach that. So that's why I started looking for alternative tools, and they could be of many different kinds. Either try to do it with quantum computers, this is what Aaron is doing, or I'm doing it with classical AI. So that's why I ventured in this direction in the first place. And back then, these are some of the problems I'm going to tell you about briefly. So back then, they all looked very similar to me. That I already told you about unknotting problem. So this is a much more complicated diagram, and go figure if it's unknot or not. And we have to disentangle it. That's a non-trivial problem. But again, there are three basic moves. So one can formulate it as reinforcement learning problem and see what happens. And I'll show you in the next slides what happens. Then some of the really interesting questions are close cousins of it. For example, deciding if knot is so-called ribbon or slice. These are important notions in low-dimensional topology. Is very much like this, except you add one more move. So it's pretty much the same thing. And another thing I'm going to tell you about is something about Andrews-Curtis conjecture. That's from combinatorial group theory. It actually looks very much like this problem, but algebraic version of it. And by the way, at any point, feel free to raise hands, interrupt, or ask questions. Another thing that I want to advertise is all of these projects are like open source, so you're welcome to check out papers or GitHubs and download code and play with it. Okay, so my goal is to explain hardness. So first I'll explain it from this point of view, which is what came out of that unknotting project. What happened is you train this model, you train the agent, and see the performance improves, it quickly approaches 100%. So typical thing, and that was our reaction back at the time, to celebrate, because this looks good. I mean, if you train or throw more compute at it, it will be like asymptotically 99% and so on. But now, so that was 5 years ago. Now, if I look at graphs like this, and these are typical graphs you see in ICML, NeurIPS papers, and computer science, I ask a very different question. I'm not necessarily happy, not because I'm old and grumpy, but because there is something interesting here. That this epsilon, however small, you can ask, is this epsilon just a statistical thing? And some unknots consistently, or some unknots, all unknots get solved 99% of the time, and some of them just sometimes fall outside. Or are there some unknots which are consistently hard? In other words, is this epsilon, like statistical average, what's the distribution in our sample that we're exploring? So if there are hard ones which never get solved, then it becomes interesting. Then it means that what it shows me is that it does well in generic case. But if there is an interesting tail, then it's probably not finding what I wanted to find. So that's kind of question that I wouldn't ask back then, but I'm asking all the time right now. So here's another lesson. That's another thing from that same paper. So once you train these agents, like I said, you have to build your model. So I'll make this point several times in this talk. You basically go and build your own custom model for this problem, and I'll explain why this is important. And it's like building a car. You have to choose engine, you have to choose frame, and so on, all the major parts. So let's think about engine being the algorithm. So I already mentioned DQN, which is a very basic one. It's very reliable, very cool. But so that stands for Deep Q Network from DeepMind. But these days, there are quite a few other ones. Maybe there are a dozen or a couple of dozen very standard ones. In typical machine learning course, you learn about 5 of them. But if you're industry grade researcher, you probably know about a couple of dozen. But most of them are off the shelf and so on. So you choose your engine, whatever you think suits you. And this is what we did in this project. So here, there are 3 types of points in this graph. So braid length is roughly number of crossings in these knot diagrams. And again, vertical axis is performance. So it shows you how well things are. So of course, you want to see things close to the top. That means good performance. So RW stands for random walker. So this is an agent which makes random decisions. And probably, well, at least I learned from my childhood, random decisions are not good. So yeah, as complexity grows up, nothing good happens, it quickly plummets. So A3C is asynchronous advantage actor critic. It has 3 A's in a name. That's why it's A3C. There is another one called A2C and so on. And this is pretty good algorithm. It's slightly better than DQN typically. And as you can see, for reasonable number of crossings, it hovers around 70% and then goes down. And then there is this one, which is trust region policy optimization. That's another algorithm. That's another choice you can make in building your model. And this is considered slightly bulkier. It requires more compute typically and is more interesting. And not surprisingly, well, here it performs well. It again grows to all the way to 90%. So, okay, again, back in the day, we had this graph. It's actually from the paper, and we were very happy about it because, well, we did what people do. We experiment with several options. We find the one that works. And if it works, we publish a paper, right? I mean, very cool. But now I ask the following question. So we are trying to apply machine learning or AI to our really hard math problems. So what are the chances that 1 out of 20 or 30 off-the-shelf algorithms is ideally suited for my particular problem? What this graph illustrates is that chances are 0. Because what it shows is that different algorithms perform differently. And the fact that in the space of algorithms, in this big C, some 20 pre-selected points which have their acronyms and so on is ideally suited for my problem, come on, that chances are small. So what I have to do, this is another interesting lesson, is what one should really do is continue iterating. It's not a bad idea to start with off-the-shelf model, but then one needs to customize it. That we need to continue exploring and build custom AI models that would really perform well on hard problems. That's one of the lessons. Any questions?
Should I find it very strange that blue dots increase towards the top right? Shouldn't they? I would expect, like the other algorithms, they would do worse as you add more longer braids.
Yeah, that's interesting. So in fact, the same could be noted here as well. So N here is braid length. And what you notice is that as braid length increases, the performance gets better. So in the paper, we didn't do super careful analysis of it. We have some discussion. And this interesting phenomenon, it's interesting. So part of explanation could be that it's like when you're playing chess with a stronger opponent, you get better. So maybe that's part of it. Right? I agree. That's interesting. And here, yeah, same thing. So it dips a little bit and then only goes up. Good point. Other questions? Okay, so I promised you algebraic version of this unknotting problem or problems. And this is another cool thing. This is a pretty cool problem. So it's open for 60 years. So it scores pretty well on this board of open conjectures. And it's fairly well known, in fact, in several domains. It's kind of at crossroads. So it's well known in group theory. That's where the problem belongs. But then combinatorialists know about it, and low-dimensional topology, there are some connections, and maybe I'll show why. And the problem is the following. So you're given a presentation of the trivial group. So you may laugh at it because, well, I promised group theory, but trivial groups are trivial. So what's there to do? So it's actually about free groups. That's the right way to think about it. So, but anyway, so somebody tells us that we have a free group. So trivial group. We already know this. And it has n generators, x1 through xn. And then we have some number of relators. And it's important that number is equal to number of generators. Such presentations are called balanced. So relators are basically words in X's and their inverses. So it's already maybe suggestive, oh, maybe we should give it to LLM, right? Because LLMs are good with words and language and all that. So anyway, the problem is to start with some presentation, which we know is trivial, like Oracle or God tells us that it is, and then find a path. Again, keep in mind analogy with many of the other things I was explaining, like path in a sequence of randomized modes or path in a sequence of lean steps. To presentation, which looks really trivial, where you don't have to worry about whether it's trivial or not, you see it with the naked eye, namely your relators just kill the generators you introduce. And the three moves you're allowed to make, think of them as analogs of randomized moves, are various multiplication of relators, inversions, and conjugations. Okay, so again, I mentioned before that reinforcement learning loves it when there are a few basic moves, like basic moves of joystick and so on. State space is pretty large because it's basically characterized by how many words this could be. And there are two versions of the conjecture. Both are open. One is with these rules, and another one where you're actually allowed to change number of generators and relators in such a way that you keep things balanced. And by introducing generator and then killing it. So this is called a stable version of this. AC and Curtis. Pretty cool conjecture, again, open for a long time. And that's what you can try to tackle with, again, reinforcement learning. So it sounds perfect because large state space and so on. This is brief history of the universe of this Andrews-Curtis conjecture. There are lots of interesting developments along the way. Agbulut-Kirby, two topologists introduced very simple looking set of potential counterexamples. I'm going to show you these counterexamples on the next slide. This illustrates that there are connections, synergy with low-dimensional topology. So in fact, quite a few things come from low-dimensional topology. Their family of counterexamples was then generalized by Miller and Shoup into a much larger family. And here I also mentioned this work of Mesnikov, and Spielrein, which is relevant to stable version. And what's interesting, the reason I mentioned some of these milestones is that each one became kind of subfield and research area of its own. And that's where we started approaching this problem with Andrews-Curtis, or with machine learning, sorry. Okay, so first, what's known about this conjecture? By brute force, by direct search, people explored potential counterexamples, and for various presentations up to total length 13, they found that there are no counterexamples. Total length means that you express your relators in terms of generators, and then adding up the length of generators gives you the length of such presentation. So up to 13, there are no counterexamples, so that we know is true. Nevertheless, conjecture is believed to be false. Actually, that's what I learned when I started working on this. Now I have no idea why it was believed to be false. Once I approach all the experts and then really try to challenge it, they say, well, we have so many potential counterexamples and we can't rule them out. They seem to be hard. So most likely one of them is a real counterexample. That's the best. That's actually most of the answers. I promised you Agbulut-Kirby series. This is very simple looking family. It has only two generators. Not like in the previous slide where we had multiple generators. It had only two generators, X and Y. That's it. One relator is always fixed. It's braid relator on this X and Y. Another has very simple form. Y to the N equals X to the N plus 1. So when I talk about length, this would have length 6 because there are 6 total letters. This would have length 2n plus 1. So the total length here would be 2n plus 7. of the presentation. So it has connections to low-dimensional topology. For example, validating any of these counterexamples would disprove this generalized property R, which is a very cool thing. Low-dimensional topologists love usual property R, which was proved by Gabay in '80s and generalized in various ways. So then in '90s and early 2000s, people proposed and then quickly refuted various generalizations. And this is the one coming from the work of Gomf, Charleman, and Thompson. In fact, I mentioned it in one of the previous slides, which still stands, and that's the one that people try to prove these days. Most of these connections to low-dimensional topology come from thinking about generators as being one-handles, generators of the group, and relators as two-handles. So that's very naturally. In fact, that's how we build fundamental group, pi 1. And since we talk about group being trivial, we're talking about four-dimensional objects with a trivial fundamental group. This is where connection to smooth Poincare conjecture in dimension 4 comes in, because that's basically asking if what looks like a sphere is actually a sphere. And in fact, every such balanced presentation for the AC conjecture gives potential counterexample to smooth Poincare conjecture in dimension 4. So this Agbulut-Kirby series, we actually, for most values of n,
does it give a counterexample, or does we say
potential counterexample?
not necessarily?
Not necessarily. In fact, I'm going to illustrate precisely this point. So in this Agbulut-Kirby series, for n greater or equal than 3, we have no idea. If these are potential counterexamples which we cannot trivialize, we cannot bring them to the form xy, and then here xy, using this basic move. And again, this is just two generators. But Gomf showed that for n equals 4, you can actually reduce it. You can show that this is not a counterexample to SPC4. But because implication is only this way, it still, so this Agbulut-Kirby 4 still stands as a potential counterexample to Andrews-Curtis, but not to smooth Poincare conjecture. So implication is 1. And again, when we say potential counterexample, it means that we haven't found a way to like trivialize it. Does it make sense? Okay, looks like nice game. So then you can, build your agents, start training them. You see training curves and many of the things I've showed you before. And this is illustration of how it works. So you collect some statistics. For example, you try to see distribution of your solutions. And I already primed you in the earlier part of the talk that paying attention to distribution of hardness is an important thing. And you quickly see that for trivialization path, which could be several hundreds here, notice that this is much longer path than you typically encounter in games like chess. You see that a lot of data sits somewhere here, but sometimes there are these outliers which shoot off a bit higher. Okay, so you already notice that in distribution of your examples or data, there is something slightly uneven, that there is a generic case, and then there are some outlier cases. Okay, so it's not going to be very even. In fact, Martin Britson, so he's director of, president of Clay Institute, and in his civilian role, he worked on this Andrews-Curtis conjecture, and he showed that there are presentations that can be trivialized. So you have A, and you can reduce them to B, which is a trivial one. There is a path, it exists. But he showed that there is a lower mathematical bound on the length of this path. So in particular, he showed that they can be super exponential in the length of the original presentation. So for instance, this example here, which feeds on two lines, would require 10 to the 10,000 steps to trivialize, at the very least. That's the minimal mathematical bound. So it is trivializable, path exists, but you have to make 1 and then 10,000 zeros number of steps. Okay, it's not just 100 steps, not a billion steps. This is astronomical number. So the question again I'm asking in this talk is how AI systems can do that, right? So that's the question. The reason I'm asking this question is because all of these cool things that we read and hear about, they play this kind of games. And average game of chess is only 30, 40 moves. The hardest and longest game of chess at least recorded in professional history, is 269 moves. So in games of chess, which we think are hard, the difference between, first of all, these games are short. It's like 30 moves or 300 moves, not one and then 10,000 zeros number of moves. And also the difference between generic case and the hardest case is hardly noticeable, just one order of magnitude. The same goes for the games of Go. There you can have a couple of hundred moves on average game and maybe a couple of thousand moves on the hardest game. But again, these are short games, and the difference between generic case and the hardest case is tiny. Whereas what we see here, for example, in many of these problems I showed you, including Andrews-Curtis conjecture, and thanks to Martin Britson and there were other works by Lishak and others, what happens is that you have the sea of generic cases where, given the length of initial state, you can find your pathfinder finds this number of steps being polynomial in this original length and reaches the final goal and destination. And then small variation, almost hard to notice variation from these states, gives you something which immediately becomes super exponential in complexity, 2 to the 2 to the 2 like L times. Okay, that's actually what happens in this Andrews-Curtis problem. So how can you train AI, which is very good at finding generic things, to recognize this needles in a haystack? And these are now very important because these are really cases you want to find. So this is actually a good question. It doesn't exist. I mean, the answer to this does not exist in AI research. So that's what excites me, and that's the main message of the talk, that trying to solve these hard math problems, now what we have to do really is to roll up the sleeves and start doing CS. I mean, we have to build these algorithms because they don't know how to do. So you can ask, okay, what people have done in CS to address this? Earlier, remember I told you about history of this DQN algorithm coming from DeepMind, DeepQ network, which worked on Atari games and so on, and it worked really well. And when we say that, we usually focus on upper part of this diagram, which lists performance for different types of Atari games. So here you can see Pong, tennis, James Bond, Kangaroo. I have no idea what these are, but anyway, this is human level performance, so many of them are above here. But let's look here, okay? So one game got exactly 0 score. It means that this DQN never succeeded to get a single point in this game, okay? Its name is Montezuma's Revenge, okay? This happened back in 2013, and actually for reinforcement learning community, for AI community, this became an obsession. So it became a nice benchmark to train models which can actually bring it ideally to this level or maybe higher. And look what happened. So this is plot for figure 6 from one of the papers which actually managed to solve this problem or build such an algorithm. But look how many groups tried and failed, right? This is very much like startups in Silicon Valley, right? Many of them fail and then like one succeeds. So that's a typical story. To me, this illustrates something else. I told you that it's a good idea. I mean, we were discussing like, what are the chances that some off-the-shelf algorithm is ideally suited for my hard math problem? My point was chances are 0. And this illustrates it really well, that for harder problems, you have to build custom algorithms which are really tailored to that. And here it took about 10 years for people to start with DQN, then go to various versions of DQN, like you see various things added to it. You see A3C that I talked about, PPO, TRPO, and finally something started happening here, okay? So you had to go through a bunch of algorithms, your own custom ones, before you discover something that works. This is actually my experience in applying ML or AI to hard problems like Andrews-Curtis. So you become like a research lab, you have to go through lots of things, and it's not a bad idea to start with off-the-shelf things, but they probably won't work. So what's important is to learn lessons why they don't work and keep iterating the process until you learn. And that may be a couple of years until you succeed, or a couple of hundreds. We talked about, so by now you see where I'm going with this. So hard problems are like needles in a haystack. They're sparse, they're very hard to find. And even in earlier days, there are benchmarks called needles in haystacks. So since I'm talking about needles in haystack, I feel obligated to show this. They were applied to LLMs, and lots of red here indicates that LLMs are not really good at finding needles in haystack. You probably have some experience with this yourself, because if you ask LLM a question that many people know or generic enough, again, generic part of the distribution, you're probably going to get reasonably reliable answer if you try several times. But if you ask something super specialized, again, think about outlier in the tail, needle in a haystack, not really good. So I'll illustrate one of the things we tried. So for instance, in this Andrews-Curtis conjecture, so it's a real question, like how can you overcome the super exponential length that it needs to work with? So first step is very easy and obvious, is that you have to start aggregating basic moves, basic steps that agent is allowed to make into chunks. Let's call them super moves. This is not such an original idea. In fact, if we're thinking about finding a proof of a complicated long theorem, it's natural to break it into lemmas and so on. The main question from AI point of view is, how do you break it into lemmas? And in RL, I already showed you the usual cycle where agent interacts with environment, collects rewards, and continues. But in usual RL, in fact, none of the algorithms I mentioned allow you to change action space. Whereas this would require you to start throwing new things into action space. So this is already pretty cool. This is already like outside of traditional RL. It's developing new things. So at the very least, you have to have some kind of multi-agent system where part of the system plays the game on your chessboard, and another part of the system decides how you actually change rules of the game once in a while. So and that became crucial for this Andrews-Curtis conjecture. So in particular, the way we implemented it in that case is we try to make these changes to the action space. One thing we learned very quickly is that making changes too much is too confusing to the system. So you should once in a while, quite rarely, add and also remove things. Removing is also important because if you add too many actions, it explodes, and that's also not good for learning. But then main question is, how do you add the super moves in the action space? And one metric for us was something that allows you to solve a problem that has not been solved before with longer presentation path, which is, longer solution, basically number of steps, here shown in red, is what you add as a next super move, or you have some policy on how you select a super move from such new harder cases. So you have to have some metric of hardness to make it work. And again, in Andrews-Curtis, it was number of steps that solution requires. And with this, we actually managed to do a couple of things. So there are lots of theorems in the paper. I'll show you one and explain where it came from. So first, we implemented this dynamic action space with supermoves. So that was new algorithm. Now this paper is published in Europe. So it's useful for AI research, obviously. But we were actually, so a couple of things happened. So first, we had this family of, say, Akbulut-Kirby presentations, which was open in its own right for more than 40 years. And this remained like a Mount Whitney, really hard thing to climb. And we managed to make progress on presentations with small values of n, for example, n equals 3, 4, 5, and so on. And then actually some miracle happened. So we were analyzing the solutions that AI found using this tool. And in general, it doesn't have to be interpretable. So for example, solution for n equals 5 could be very different from n equals 4. But what happened here is that there was a pattern. And based on this pattern, we were able to white box it, extract like C4 is for the trees. And this is just luck. So honestly, this didn't happen. But then we were able to interpret it and prove a theorem for all n, which of course in mathematics is the right thing to do. It's cool to like address one example, two examples, but we usually want to prove theorems for whole family. So here, for the first time, we were able to reduce for the entire family complexity or difficulty of this from 2n plus 7, which was our initial computation, almost by half, to just n plus 11. And that's something that's very cool. So some of these presentations required making 1,500 steps. So again, think about how it compares with games like chess and Go. So you have to really go pretty far in searching for these things. And I want to close this talk by saying that my whole point or topic here was that hard math problems are like needles in a haystack or unicorns, or in financial markets, you would call them black swans. These are rare phenomena which cause disproportionate disruption or cause reward. Think about like extreme weather phenomena or financial market crashes. And what we're doing is basically we're trying to approach such challenges of finding needles in haystack or black swans through mathematical problems, because many hard math problems require AI systems to look for these rare instances which are sprinkled in the sea of generic cases. And this makes me paraphrase this nice quote by Vladimir Arnold, who said that mathematics is the part of physics where experiments are cheap. So I want to rephrase it that mathematics is the part of AI research where we don't have to experiment with financial data or weather data. We can actually use math as a framework to develop such systems which find needles in haystack or black swans. And then hopefully they could be useful for other domains. So thank you for your attention.
Oh, questions or comments?
So is there a way to formalize the algorithm of selecting the super moves within the, like to make just an agent-based learning that builds super moves on the way? Is that?
Well, ideally, yeah, so it becomes a question indeed, how do you build such a thing? So how does it select super moves and so on? And it's a big challenge. So we managed to do something for this particular problem, but
So I guess the point is there you have outliers and then a proof of the outlier, not like why it is still an example. So then you can take that as an input into the, and I guess you're making that part like algorithmic is probably pretty hard. For if you wanted to have like a general purpose algorithm that helps to select.
Well, I think that's part of the reason this is interesting even for like AI researchers and published in Europe and so on, because there is cutting edge. I mean, there are no such algorithms that allow you to do this. So there is no science about it. And that's why it's cool. So we build one model, but I think at least our attitude in this lab is we have to build 5, 10, 20, and then we start seeing forest for the trees, how to select the super moves. Because similar problems arise again in trying to decide how to break, I don't know, proof of Riemann hypothesis in sub-milestones, right? And the sub-goal generation is a very hard open problem for AI research. I mean, that's one of the cool problems. It's like Riemann hypothesis for AI research. So we're just making one modest step into.
More comments or questions?
I've got a question, but I think it's a bit hard to phrase. So a lot of this talk has been about how, as you say, you kind of have to basically design your own model to solve a lot of these things, right? If you want a really good model for solving the task at hand. So in the future, how do you see this impacting how, like who, I guess, solves really hard problems in mathematics? Like, does this mean that in the future, it's going to require so much compute to train these truly state-of-the-art, extremely narrow, fine-tuned models that the only people who can actually solve problems like this one that you were talking about are really large AI companies? Is that what you foresee?
Not at all, not at all. In fact, yeah, thank you for the question. It's a very good one. Sometimes I mention it and today I didn't, but thanks to the question I will, that much of it can be done with fairly modest compute. So some companies prominently feature idea that scaling is enough. So scale compute and for example, XI is amazing at building like biggest and quickest data centers and all that. But all the scaling curves, so there are several scaling laws usually people talk about how your performance scales with amount of compute, size of the model, and also size of the data set. And all of these curves are logarithmic. And logarithm is a very slow function. And if I want my performance to be like 10 to the 26 or 1 in 10,000 zeros, okay, take exponent of that. And that's how much we have to scale compute. And it's just in physics. So at least to me, this says that compute alone probably will help, I mean, scaling. But here I see that we need ideas. We need research. And Aaron was asking, like, how do we choose the supermodes? And I think that's where we hesitate. Currently, if I go to NeurIPS, people say, oh, this is a cool problem, but I have no idea how to approach it. So that's where we are. So I think we need ideas. We need AI research. And most of what I showed you, the way it works is you prototype everything on a small compute on your laptop. Then you can get, I don't know, hundreds or maybe a couple of thousand hours on cloud. And then scale if it really works well. So that's a typical progression. But I don't think you need millions or billions of GPU hours to make it work. At least my hope is that modest compute is enough. So, and that's why I think I showed single GPU and like proving of this there. So at least that would be my hope. But maybe I'm wrong, by the way. I
Questions
should
or
also say
comments?
there is a scenario where I could be wrong.
Well, I notice you have Vladimir Arnold and you have fluid dynamics sitting there. And none of your discussions impacted on basically PDE type problems. Do you think that's sort of a different sort of subspecies of mathematics as opposed to something like low dimensional topology?
Yeah, so character of problems is also a bit different. So yeah, thanks for asking about Navier-Stokes. I think that's all what we're thinking about. If I were to make a bet, I would predict that that's the first Millennium Prize problem that is gonna fall to AI, but for various reasons. And one of them is that much of analysis is not in Mathlib. So, and therefore, it may be slightly easier to cut corners into building it geared to a particular type of solution or problem that we're trying to solve. Anyway, I'm not going to go in too much in that direction, but you're absolutely right that here the style was very clear cut, like combinatorial playing game where moves are typically discrete and so on. There, the types of problems are slightly different indeed. Especially if one is looking for counterexamples where there is a blow up. So people, of course, famously use this physics-informed neural networks, PINs. Now there are even cooler things on the market. So it is indeed slightly different. But if one wants to find a proof, which is a sequence of, say, lean steps, then it would be very similar to the search type of search I'm talking. David, you had a question or?
Oh, it's a back to the question earlier, while, when those kind of basic algorithms were performing really well, with the bright length. And, you said, well, presuppose that, maybe like us, they're harder to challenge, or the challenger, the more you learn. But so we really have no clue why they perform better at that.
I have no clue why. I'm sure. So that's another thing that I learned over the years, but I didn't do 7 years ago. It's always a good idea to, before building next step, think about why certain things happen. And I fully confess that back then I didn't do my homework well enough to be able to answer this question. But so I'm sure there is a real answer, which I just
Okay, yeah. So, but people know. Okay.
No, I don't think people know. I think again, I haven't followed it yet. At least me and my co-authors don't know, but and I don't think it's being looked at. So I think it's a good. But like I said, I already confessed to making many operational mistakes and being too naive about the training curves.
Yeah, with knots, there's a lot of weird bad intuition you get if you study knots with less than 20 crossings. Like almost all knots are, or you get a lot of alternating knots at the beginning, and then eventually they're like very rare that you find alternating knots. I've discovered this also. When you compute everything that you can do on your laptop, you get a very skewed view of the world of knots.
Well, let's thank Sergei again for this.